Good afternoon, everyone. Thank you for inviting me to present at today's symposium. It's been wonderful to see all the team's work that's been showing this afternoon and this morning so far. In this talk, I want to share with you work we're doing on using wearable motion sensors and computer simulations to support humans in space. So earlier today, we heard about habitat development for humans and visual augmentation to support the human. Here, I want to share a little bit more about designing missions and assessing spacesuits. I'm going to try to monitor the chat window as I go along. So please feel free to ask questions as I'm speaking, and I'll try to look over there. And you're also welcome to ask questions at the end. So I don't have to convince anyone here about the wealth of knowledge that is learned from the engineering to go to space or the science we get from space. Human space exploration provides us with knowledge of our planet, the moon, and the universe around us. For terminology, though, in case some are not yet aware, when an astronaut is outside of the vehicle, it's called extravehicular activity, or EVA. So these images that I'm showing are from Apollo 11. And what you see is Buzz Aldrin on the left, and on the right, Buzz is carrying two experiments to set up. A passive seismic experiment package is one of the instruments that he's holding. So these seismic experiments provided information about the layers of the moon, and rocks that were collected provided information ranging from elemental composition to how the rocks were formed. So then the question is, well, why should we send humans to space? Well, besides the natural human desire to explore, there are reasons why humans should stay a part of exploration. While there's been a lot of exciting progress that has been made in robotics in the last few decades, there are still areas where the human can perform better than is possible with a robot. So a robot can be made to perform tasks to very high precision, enabling repeatable performance. Advances are also being made in robot online learning and decision making. However, humans currently are more flexible in decision making as they can update plans more easily for novel scenarios. They have better pattern recognition when there are limitations in lighting or changes in viewing angles. And humans also have the flexibility and their dexterity to manipulate objects of widely different sizes and shapes. So the coupling of humans and robots together provides exciting opportunities to support the humans on tasks to prevent fatigue or to ensure precision, while the human can lead the decision-making related to the sites and objects of interest. So as an example, here are three scientific interests on the moon: exploring craters, permanently shadowed regions, and volcanic terrain. Permanently shadowed regions are those regions that never see sunlight and have a lot of additional considerations when you start thinking about design. And you heard a little bit about some of these permanently shadowed regions from the survey presentation a little bit earlier. Now, the determination by geologists of where to sample is based on perception of textures, coloration, and material compositions to enable them to attain the samples relevant for their science. So while the part of the goal of space exploration is to get somewhere new and develop the technology to do that, the other aspect is to conduct science and to learn new answers when we get somewhere. So we have to be able to design these missions and the tools and suits supporting the human in order to get that science completed. So as I mentioned, part of this is designing the suit. The suit is important to protect the human from the harsh environments. The moon has a scant atmosphere and is considered to be surrounded by a vacuum for all purposes. Spacesuits are required to enable the astronaut to breathe, enable temperature regulation, and prevent injury from small particles traveling at fast speeds, since there isn't an atmosphere to slow it down. The image I'm showing you here is Harrison Schmitt, who is the Apollo 17 lunar module pilot. He's collecting lunar samples using a rake-like tool. So one of the other things is that this suit needs to allow mobility to achieve the goals of exploration. And when it doesn't allow that appropriate mobility, we need to be designing tools in order to enable those tasks to be completed. So when considering mobility, the astronaut needs to be able to walk, crawl, climb. They need to be able to go up and down slopes to travel away from a lander. And they also need to be able to carry and use tools. So as we heard mentioned earlier, NASA's Artemis mission has the goal of going to the lunar surface by 2024. The first phase of Artemis has multiple parts, including sending a spacecraft to the moon, then having humans once again orbit the moon. There will be tests of new propulsion systems and landing systems. And the final part of that first phase is to have a crewed mission to the lunar surface. And then Artemis phase 2 considers even more human exploration. However, there's many open questions that NASA has for sending humans back to the space environment to conduct scientific research. NASA keeps a list of these gaps that are needed to be addressed to successfully complete a mission. I want to share with you some of the gaps related to performing EVAs that are related to wearable systems, which is one of the things that we do in my lab. Then I'm going to share with you some example projects that we've looked at using wearable systems to address these gaps. So the first gap is related to EVA crew required capabilities. So one of the gaps is that the physiological and cognitive performance capabilities that are required of crew members are not adequately understood. So human performance results have been very different between people who are performing the same task in the same EVA suit at the same gravity levels. NASA wants to characterize how mobility varies across operators of the suit, considering how different strength, body shapes, and other factors influence this motion. Classical motion capture systems use cameras that can measure how the suit moves, because these cameras can be placed around the person in a controlled research environment, but they cannot measure the human inside the suit. So using wearable motion sensors on the human in the suit gives us this opportunity to see how the human is moving to drive the suit motion. The second gap that I'll highlight is EVA ConOps, so concept of operations for human health and performance. EVA task design and operations concepts are not adequately understood. Future exploration missions are expected to have more planned EVAs than ever before. So in NASA history, a single astronaut has never performed more than 3 surface EVAs or 4 microgravity EVAs in one mission. Some design reference missions for exploration have astronauts performing almost daily EVAs over many months. So it's going to be important to determine if workload or work rest cycles, EVA frequency, or EVA duration have an effect on short-term and long-term crew performance and health over the exploration missions. One way to consider this question is to look at current field scientists on Earth to understand how they allocate their time during long field expeditions, to use this information to inform how they perform their science on Earth and how we could extend that to performing science on lunar surfaces or other planetary surfaces. The third gap is quantifying suited mobility. Consistent and validated methodology does not exist to assess the mobility of a spacesuit at the integrated level. So there are efforts to use wearable motion sensors in a consistent way across multiple systems to make these comparisons of mobility. And we want to do this because we want to understand suit design. So the last EVA gap is EVA suit design for human health and performance. The effective suit design parameters on health and performance are not adequately understood. So with a good way to quantify suited mobility, we can have a better understanding of how changing suit design parameters affects performance, including the ability to achieve the ConOps goals for using tools, collecting samples, and traversing the moon. Okay, so in one of the projects that I'm working on, we're collaborating with researchers at NASA to characterize scientists in the field on Earth to understand the mobility needs for the scientists, as well as the allocation of time to different types of tasks. Our initial effort has focused on both the cognitive and the physiological side of the goals that they have for these missions. We have an array of wearable motion sensors that are placed on the scientists, as well as having audio and video information. And then we're developing automated procedures to understand the activities that are being performed. So I'll talk a little bit more about how we do that. So there are several ways we can think about the activity classification of a scientist. Consider a general motion signal. So you can think of this as an acceleration or a velocity, for example. We can use wearable motion sensors to detect movements. So that's one of the spaces that we're interested in. For example, is the person standing or walking? We can use wearable sensors to detect postures, such as if someone's upright, kneeling, or bent over. And then another important thing to understand is what tools are being used and when. We want to know when they're using their hammer or reaching into their backpack. So by understanding this movement, posture, and equipment space, we can infer what type of task is being performed and how time is allocated in the field, as opposed to simulating these tasks in a lab where they're not truly doing the activity, but they're just trying to mock up that activity. Okay, so I'll just share a little bit more about some of our early results from this type of analysis. So the posture space is defined by the different poses. So in this case, we were looking at upright, bent over, kneeling, and crouching. And here I'm showing an example from one scientist and the number of times they transitioned from one pose to another. So this scientist transitioned between bent over and upright 223 times, which is 42% of the transitions observed. Now, interestingly, the spacesuit does not actually support bent over. The suit permits upright and kneeling. So this information means that either the suit needs to have this feature added, or if not possible, tools need to be developed to support the scientist so that bending over isn't required for the task that they need to achieve. So earlier I showed you a picture of a lunar rake. This was an Apollo era tool to support sampling without needing to bend over. So as we start thinking about what the scientific tasks are going to be for these lunar missions, we have to similarly think about additionally what types of tools need to be designed. So scientists perform many different kinds of movement, but for the purposes of developing ConOps, we wanted to know when the scientists were stationary, walking in their local environment. And so by walking in their local environment, I mean they want maybe a different view of the same region, but they're staying in the same general vicinity. Or when they're geospatially relocating to a different area. Also, within that stationary period, we want to know if the person is completely static, so maybe they're just thinking about what they've seen or planning, or if they're partially static. And by partially static, we mean that they may be using their arms or torso, but with their feet planted. So they're performing some kind of activity, but in a single spot. So we found that for the scientist I'm showing you, there's a large portion of the time where they're partially stationary. So they're working at a given site. This scientist during this period of time spent about the same time reorienting in the vicinity of the site as they did moving between different sites. And being able to understand timing is important for ConOps development, as there are assumptions made as to how long it takes to do particular tasks and how tasks can be stacked within a particular EVA. These data also support understanding the energy costs of the astronaut and what their oxygen consumption will be for certain types of planned activities. As new technologies are added to the process, it's also important to understand whether the technology will add time or save time to these estimated tasks and how they will support those mission goals. The final space that we've been looking at is the equipment space, and it's defined by the interactions that scientists have with tools that were previously identified as being critical for fieldwork. While tools are typically designed for a specific purpose, scientists use tools in a way that were unintended by the initial designers. So we have tools and recorded the way in which they were used and when they were used. The image shows an example of the acceleration measured for a hammer. Using the sensors, we can tell when the hammer is being used in different positions and different tasks. One of the EVA questions of interest is which tools to attach to the suit versus which tools to place on rovers, base stations, or in a carrier for the astronaut. Understanding tool usage frequency can inform where tools should be placed. Also, understanding tool versatility can reduce the number of tools required and save space for what the astronauts need to carry. So in that previous project, we looked at functionality needs for the task. However, we also need to consider how the spacesuit fits in order to perform these tasks. The idea of dynamic fit refers to how the human and spacesuit move and interact with each other during a task. If you look at this image I'm now showing on the left, you see a model of the shoulder showing how the shoulder shape changes as the arm moves. So you can actually just kind of move your arm around and you can feel yourself how this shape changes. So when the suit is designed, designers need to enable the arm to move through space that allows for these shape changes. So this image in the middle that I'm showing highlights the idea of fit for the leg. When standing, my knee joint may align with the suit knee axis. However, as I bend my leg, the relative alignment may change. For example, if my foot starts to slip out of the boot, as is shown in that right image, the knee axes can become misaligned. This can make movement more difficult and can also create potential injury risks. One potential injury risk could be chafing of the foot with respect to rubbing on the boot, but there could also be other injury risks just from how you're moving and driving the suit based on the leg being misaligned. So we have used IMUs on the outside of the spacesuit and on the human inside of the spacesuit to estimate this idea of dynamic fit. We've observed that the suit reduced the knee range of motion when walking. We also found we could observe relative motion between the human and suit and show when the human was moving within the suit. There were certain design configurations we saw that could decrease this relative motion. However, research still needs to be performed to understand how much relative motion is good and helps performance versus maybe is bad and decreases performance. So this is still an open question of what does it truly mean to fit? While spacesuits provide protection and need to provide mobility, there's also this concern about different types of injuries that can occur when wearing a suit. For the consideration of fit, I mentioned injuries from rubbing between the suit and the human. However, there are also forces that are placed on the person due to the suit. The spacesuit technology that we were working with was the Mark III spacesuit, which is a technology demonstrator, and it weighs about 160 pounds. The spacesuit supports some of its own weight through its structure. However, there are also shoulder straps that help stabilize the astronaut in this suit. These straps are also elements through which the weight of the suit is transferred to the astronaut. We previously measured that the transferred loads could be between 20 to 50 pounds per shoulder. So what we did is use a computer simulation to examine how these loads affect spinal compression and potential for injury. So what I'm showing you now on the left is spinal curvatures for just different types of spinal curvatures. So our curvature can be different across people. And one of the questions we were interested in is how does spinal curvature affect this spinal loading? In this middle image I'm now showing you is our musculoskeletal model. This just means our model of the skeleton system and the muscles that connect to the skeleton that are used to create and stabilize motion. Now on the right, I'm showing you example results where on the x-axis, it shows you the vertebral level. That's the spinal location. So the L's are the lumbar region, and you can see where the lumbar region is that lower part of your back from that image on the left. The T's are the thoracic region. So that x-axis is really showing the spine from the top to the bottom of the spine. And then the y-axis is showing the estimated load at that location. Now the colors are showing three different loads: unloaded, 20 pounds, and 50 pounds on each shoulder. And the shapes, that circular star, are showing the curvature. Here I'm only showing you two of the curvature conditions just to simplify the chart a little bit. And what you see is that as we increase the load on the shoulder, we see an increase in spinal compressions. And we also see that when the spine has more curvature, this location of peak force moves from the lumbar region to the thoracic region. In this study, we found the loads don't approach spinal loading limits that would create fractures, which has been shown to be between 8,500 and 11,000 newtons. However, there could be increased risk of back pain, with the pain location being affected by the individual spinal curvature. And you can see that by where the peaks are. Okay, so by using wearable sensors in human experimental studies and computer simulation models, we have the ability to support several of the EVA gaps. The sensors allow quantifying suited mobility and supporting assessing suit design decisions. From the sensor data, we can also better understand scientific fieldwork and use these data to inform requirements for EVA crew and ConOps development. From the simulation data, we can assess human health and potential injury risks. There's a lot of ongoing research to support human exploration in areas including spacesuit design, tool development, and mission planning. I highlighted a couple of the projects in my lab, but there are additional projects we are working on, as well as exciting research in other labs supporting these efforts. Spacesuits need to provide life support, but must also enable an astronaut to perform their tasks and achieve scientific goals. So I want to share some additional research questions that people are thinking about. And I'm only going to share a few sample research questions that are for supporting human exploration. So one question is, what injury risks exist and how can we minimize them? Another question is, how does spacesuit fit actually affect task performance? We want to maximize the astronaut's ability to perform the necessary tasks in an acceptable way. This question also leads to additional questions, though. How do we measure performance? How can we measure fit? What do we even mean by performance? Some tasks require a person to be dexterous and manipulate objects. Others may require agility to maneuver around a rocky volcanic field, while still others may require specific postures to obtain samples or of scientific interest. So performance isn't just one measure, and we have to consider the tasks that are relevant to design metrics that will be useful. So all research involves a team of people working, and I just want to acknowledge the current students in my lab, as well as the alumni whose research was highlighted in the examples I showed you today. I also want to acknowledge the amazing collaborators I've worked with on these efforts. So thanks for your time, and I'm happy to answer questions that you guys have.
Thank you, Professor Stirling. That was great. I never actually got to see a lot of the work that you were doing. I only got to see a lot of the work that was kind of in the area in between, where Claus and Bliss was working. So this is really informative for me, especially as well. Yeah, if there are any questions, again, send them via the chat or raise your hand and we can unmute you.
So there's a question. What is the thinking on the best way to scratch your nose in a spacesuit? So this is a really interesting question. And I think, one of the ways that people have been just even thinking about doing something like that is you just put something in the suit that you can actually lean over and potentially touch, because your hand can't interact with your face. So I know that different astronauts have tried to address touching their face in different ways, whether it's leaning and trying to touch something. But you'd have to ask the astronauts on what they've actually done. But I think really the solution is putting something in the helmet that they can actually lean against if they need to. I guess the big concern there would be also potential injury risk on when that object is there, because if you're in an environment where there is potentials of falls or of high loads, you'd have to be careful of what objects are sticking out and potential to hurt yourself as well as to help yourself. Okay, have you done any work in collaboration with the team working on Jarvis about the ergonomics of their AR interface on a helmet? I haven't worked with Jarvis explicitly on the AR interface of their helmet. In another project that we've been thinking a lot about what AR can help you with visualization. So I didn't talk about that today, but some of the questions are not just for astronauts that are external to the vehicle, so doing EVA, but internal to the vehicle, so IVA. Where's their potential to help them on their displays? And should they just have computer screens, or should they have AR as well to interact with different types of environments and visualizations? And so we currently have a project that we're working with people at JPL and JSC, where we are explicitly looking at what type of information you can gain by having AR presentations versus on-screen presentations for anomaly detection if you were to have a small satellite go around your vehicle, to limit having the astronaut have to go external to the vehicle. You're welcome. It says thank you in the chat box. Other questions? So I'll just kind of add, when I was talking about this idea of relative motion of the human in the suit, there's this interesting question of, well, the suit has limited mobility. So do you want to have somebody fit tightly in the suit and be limited by that aspect of mobility? Or do you want them to have a little bit of relative motion in the suit as they're moving, so they gain a little bit of extra mobility inside the suit, maybe that would help them support driving the suit? And so I think that's one of the interesting fit questions right now that we don't really understand. And there's an aspect of suit fit where it's pretty qualitative right now. So I think there's some exciting questions going on right now, and just understanding how fitted do you want this system to be? And so you can think one of the areas where there's relative motion, if you have a lot of space in the leg, is as you put your foot down on the ground and you think about your leg kind of moving from behind your ankle to in front of your ankle. If the suit is fitting you really tightly, it would move with you. If the suit is not fitting you really tightly, you'd actually be moving within the suit before you come in contact with the front of the suit and drive the suit to move. So these are the types of fit questions that we're looking at. Okay, so there's a question: when using motion sensors in your research, are the sensors primarily IMU gyroscopes? What other types of sensory data is used in understanding motion? That's a really great question. Yeah, and I didn't specify which motion sensors we were using. So in the work that we've been doing so far, we are using IMUs, which have accelerometers and gyroscopes. And some of our systems also augment that information with magnetometers for some of our testing that we do. But the IMU has some limitations in that when you have an acceleration or you have an angular velocity, like you get from accelerometers and gyroscopes, you have to integrate that information in order to create velocities and positions. And so there's a lot of interesting research going on in how you can complement accelerometers and gyroscopes with stretch sensors. So stretch sensors have their own problems, but they're directly measuring position. So if you actually create filters that fuse these information together with the stretch sensors and the accelerometers and the gyroscopes, you can start to get a better overall estimate. Okay. If you fell on your back in a spacesuit, can you get up? I wish that I had some of the falling over videos. Well, I have them, but I'm not going to pull them up and show them right now, of astronauts falling on the moon. And one of the big challenges actually to some of the falling over was just that the suits in the Apollo era don't have bearings like some of the new planetary suits are being designed. And what that means is that they have a certain stiffness to them. And as you move them, it's like flexing a balloon. And they want to kind of pop back out to some neutral shape that it is designed with. So the way that it's structured, it will have some neutral shape. So as they tried to lean over or bend down, they'd have this force that was kind of pushing them back to stand up or be in a particular posture. So that was one of the things that became very difficult. So these newer suits have been designed to allow more mobility, for example, at the hip, in order to enable kneeling or to enable working on the ground. So this question on if you fell on your back, could you get up? There is ability to kind of move the body in different ways that you couldn't do with some of these Apollo era suits, but they also have tools that they're holding. And so in some of these videos, you can actually see that they're using their tool to create a reaction force to push themselves back up. So tools are versatile in what they're being used for. Okay, so there's a question of how modular are these spacesuits? If one part gets damaged, can it easily be swapped out with another? So this is a really important question that a lot of the researchers designing spacesuits are looking at right now, is how many sizes do I need? How many components will switch out? And then how many of these should I actually be bringing on certain types of missions? So how do I actually design this spacesuit fleet? So they're looking at how you can make these more easy to swap out, but there's still a concern of safety and just the appropriate timing of how long it takes to do it properly. So you may remember back to the canceled all-female spacewalk that was originally supposed to occur. And one of the astronauts originally had a large spacesuit, but she wanted to actually, so she felt on Earth she should be using a large spacesuit. But when she was in microgravity, she actually realized that the large spacesuit gave her too much relative motion, and she preferred having the medium spacesuit. So they canceled that spacewalk because they couldn't quickly change out the components. in order to give her basically the size medium. So there are some components that are more fixed, and there are some components that have these varying sizes that can then be reconnected together to recreate the sizing. So then they did change it out. She did end up having the medium fit, and they did have that all-female spacewalk later. But that is a challenge of how quickly you can mix and match these different parts and how many different sizes you have for a specific component.